Hello, welcome to our project. Our project name is Password-Based Bank Board Security System. In this project, we will implement a 5-length password system with 3 characters A, B, and C. We will use a finite state machine which will have 6 states, state 0 initially, and then it will advance 1 state with every correct input. Here we will employ a special logic which we will refer to as sequence tracking, so that even if the last input was wrong, the circuit will not reset to state 0 if the last inputs form a correct sequence. For example, if the password is set to ACABB and ACAC is typed, the circuit will go back to state 2 AC, and the rest of the password can be continued from here. If there are 3 errors, the circuit will be locked out until a must reset button is pressed from the moderator side. When the correct sequence is entered, the vault door will open and we will be able to cache in or cache out from the vault. Now we will demonstrate the simulation part of our project. Here we see a circuit properly implemented the password setting and unlocking mechanism using a finite state machine. In this part of the circuit, we will set the password using 3 characters ABC. A is 01, B is 10, and C is 11. For example, let's set the password to A, C, A, B, B. As you can see that the password is set to ACABB. Here it is where the user will type in his passwords, and using these 5 comparators we can tell whether the first or the second order, third order, fourth order, fifth order input has been typed in. Here 3 flip-flops which store the data of which state the circuit is in. Here we are implementing some basic logics so that the circuit is taking the next state or not. This button allows us to enable the special sequence tracking mechanism of our circuit. If we go to this part, this is the passwords we set earlier, and there some logics are being evaluated, and then finally we are evaluating 10 conditions which will allow our sequence tracking mechanism to work. If none of these conditions are satisfied, or if the enable sequence track button is turned off, then our finite state machine will behave normally and go back to state 0 whenever an error occurs. Here 10 conditions are being used, and the data is then encoded to 3 bits and fed back to the 3 flip-flops. Now we will demonstrate our circuit in its working conditions.
Our password was ACABB, so now we will demonstrate it. First input is A. If we press A, the machine goes to state 1, and then C, the machine goes to state 2, and then A, state 3. The next input should be B, but instead if we take C, so thus instead of going back to state 0, the state has been reset to state 2. And also we can see there has been 1 error. So we'll continue from here. We have already typed AC, and now the next input should be A and then B. Now the final input should be B, but instead if we press A, the circuit goes back to state 1 instead of state 0. As we can see, there has been 2 errors. If we make one more error, for example, next input should be C, but let's press A. And the error has been counted. So 3 errors, and now the circuit is locked. So now whatever we press, there will be no more new inputs, and the circuit goes back to state 0. We can unlock the circuit using the master reset. Pressing it, and we can see the error has been cleared. So now let's type in the password A, C, A, B, B, and we can see the circuit in state 5, and the vault door has been opened. Now no matter whatever input we type in, the circuit will remain in this state.
We come to the second part of our simulation, where we can access the bank account after the vault door has been opened. The open door is indicated by this button. 1 means the door is open and the circuit is now enabled. So we can input any value we want in this place, and we can either cash in or cash out. As we can see, there is currently no money stored in our vault. So we will enter a random value, for example 273. If we want to cash in, we will select 0, and for cash out we will select 1. At first we will try to cash out. Now if we press enter, we can see that nothing happens because there is no money at the moment, and so nothing will happen. We can select 0 for cash in and then press enter. So now 273 taka has been entered in our vault. We can input it again. We can press enter, and now it is again cashed in. Now we will try a different value, for example 517, and we can enter the money again. So currently there is 1063 taka in our vault. For demonstration purposes, we will now enter 999 taka, and we will show what happens when overflow occurs. So currently there is 9055 taka in our vault. Now if we want to cash in 999 taka, then a overflow will occur, and that is why the circuit will not take any more taka as input. So when we press enter, nothing happens.
First we will turn on our circuit, then we will set the password to ABC, so to ABC, as we have explained in the software part. Now let's look at the circuit here. This is A, this is B, this is C, and this is to reset our sequence. So we've set the password to A, B, C. If we look carefully at the sequence, A means 0, 1. So first one is 0, 1, B means 1, 0, then A means 0, 1, then again B means 1, 0, and then C means 1, 1. So the password is set to A, B, C. Now we will, for safety, reset our final state machine. Now we can see that the circuit is in state 0. There are 6 LEDs here denoting each state. Okay, now we will try all our password sequences to test, to give you some examples. For example, if we will first try the sequence ABC. A, which takes the circuit to state 1, and then B, state 2, and then C, which is incorrect. We can see that the red bulb was on, so the circuit, and so it was an error, and the circuit resets back to state 0. We will show it again. A, B, C. You can clearly see that the red bulb is on, which means an error has occurred. Okay, now we will try the next sequence, which is A, state 3, B, state 4. Now the next input should be C, but we will try A, which is an error, but the circuit will go back to state 3 instead of resetting back to state 0. So input is A. You can see the red bulb has went on, which means it's an error. The circuit resets back to state 3 instead of state 0. So we are now at the state 3, which means we are at ABA. The next input is B, state 4. The next input is C, state 5. The circuit is finally in state 5, and the door has unlocked. No matter what input we give, the circuit stays in the same state. We can reset the circuit by the master reset button, and it is back to state 0. Now we will try for another password, which is CBCAA. So we set C, B, C, A. We try these two sequences. C, B, C, and then again B, which takes it back to state 2. So we are now at state 2. We'll try the second sequence now. We're already at state 2. So the next input is C, and then A, and then instead of A, we'll type C again, which will take us back to state 1. We're at state 1. Continuing from here, we already in state 1. So the next input is B, C, A. Now the password is unlocked. We can reset the machine. In the hardware implementation of our project, we only implemented the main finite state machine part of our project. We could not implement the error counting and locking out mechanism, as our counter was not responding properly due to impulses in the system. So we only showed error but did not count it and lock out the circuit. We also did not implement the sequence tracking logic detection part, where we would evaluate 10 conditions. So we had to enter the condition manually by hand. We also did not implement the bank vault and cashing in out system. Thank you for all your attention.